Hello and welcome. Today in this oral presentation, you're going to see one machine learning algorithm application for geoscientific data, in particular for mineral exploration. This project focuses in an area in Colombia, South America. The methodology of the project is based on the workings from Fayad et al., who defined a series of previous steps before applying data mining. Note that machine learning resides within data mining. Once the steps have been applied, then we can extract useful patterns and consequently useful knowledge from our data for any particular project that we want to do. In this case, defining prospective areas. Let's give some regional context. So the project is in Colombia. Colombia is towards the north of South America, and this arrow identifies where the project is located. If we zoom into this area, we see that this black box defines the area that we want to analyze. But what about the geological setting? So for this, we have to go all the way back to the Proterozoic when we had our understanding craton, based mainly on, or composed mainly of the Guianan Shield and the Brazilian Shield. And during the Biennial Orogenic events, some uplifted terrains were created, which were called the Proto-Andes origins. If we go all the way now to the present, we see our Amazonian crater towards the right, but towards the left, several different terrains. These terrains have been identified as being amalgamated or accreted during several million years, and the ages for their accretions are listed towards in the table towards the left. Note that there's a lot of changes between subduction and extension, and this is related to interaction between the South American plate, the Pacific plate, and the Caribbean plate. This is therefore way more complicated than the setting that is found in Chile or Peru, for example. Now, this in summary identifies that towards the right, we have the oldest terrains, towards the left, we have the youngest. Now, what about, we have events happening in this area, what about magmatism? So the works from Leal Mejia et al. Identified several intrusion events or magmatism events, and linked with what was defined by Cediel et al., the magmatic trends exert a first-order control upon regional metallogenesis. This is quite important because in our area of interest, we can find several intrusions or pollutants, especially within the analysis of that in Colombia, there has been at least 5 metallogenetic events or epochs. We find that the mid-Cretaceous to Eocene and Oligocene to Pleistocene are the ones that are most relevant for us in the area of interest. These are identified by these two following maps, where we can definitely find that there is definitely deposits in the area. So we have the mechanisms, we have the source, and we definitely have the deposits in the area. Finally, we have the list of known mineral occurrences in the area, which type of mineral deposits they are. This project concentrates on porphyry, orogenic, intrusion-related, and epithermal deposits, mainly low sulfidation. Of this, we can identify that our area of interest includes the Yalcon, Tahami, and the Cacoromeral fault system terrains, which have been identified as having intrusions that are related to mineral deposits in this area. Finally, this is a cross-section of the area. We find that there is intrusions and faulting and regional faults that allow our fluids to go to surface and mineralize. So what are the general objectives of this project? First, define what are the controlling parameters of the mineral deposits in this area. Once we can find these main parameters, then we can train and test our machine learning algorithm. And if successful, then we can define target areas where we can propose further studies. So the first thing, or the first method, is then to define, or how do we define the parameters that we are going to use? This is related to the workings from McQuaig et al., where we can link the critical processes. So critical processes are the necessary processes to create mineral deposits, but since we cannot see them in place, or these are only processes, we have to find the smoking gun of these processes, which is what is called the mappable criteria. So having this in mind, for the porphyry deposits, we created this table where we link the critical processes to mappable criteria such as radiometric anomalies or geological units. However, we totally depend on what are available data we have. So all of this data was given by the Geological Survey of Colombia, where we have the magnetic data, the radiometric data, the geological units. Note that the quaternary units here have been stripped off because we identified that deposits cannot be formed here or in these rocks. Putting aside the placer deposits, we have also the structural information. This already has been translated to raster information, the mineral deposit location, and geochemistry, which is here presented as Thyssen polygons in order to show that geochemistry cannot be used to train machine learning algorithms because the distribution of this data is quite inhomogeneous, but it will be used to validate the results. So finally, having this information, which is pretty much what we want to do on the left, we finally apply data integration using machine learning algorithms and producing our mineral predictive maps. For this project, we used a hybrid approach, which is bringing knowledge. As you saw, we were applying the mineral systems approach, plus the ability of the machine learning algorithm to identify patterns. In this case, we use artificial neural networks with only one hidden layer. And the idea is pretty much in a really simple case that I present you here is if we add apples to our algorithm and train it, then if we bring a new apple, then the algorithm is going to be able to identify the apple. So that's the same thing with the deposits. If we find a pattern that identifies a deposit, if we go to some other place where we have the same pattern, then the idea is that we are going to mark this as highly probable for or favorable for deposit or the same deposit. So we base our analysis on the pixel-oriented classification, which is all the information we translated to rasters, we compile them. And for example, this pixel has the information from radiometric, structural, let's say magnetics, and so on and so forth. So finally, to extract the patterns and identify the other areas where we have similar patterns. What are the results? So the first part is for the porphyry results. This histogram identifies that the majority of the porphyry known deposits were almost properly marked as 1. And this error curve identifies the difference between reality and the prediction. So the idea is we want to reach the lowest possible error to get closer to reality. This table shows us what are the most important parameters for defining a porphyry deposit. And finally, towards the right, we have our mineral predictive maps. And we identified that there are certain areas that do identify properly our deposits, but extra areas where we don't have any deposits and they already stand out as possibly prospective areas. As I was telling you, we made a further validation with the geochemistry to understand if what we were trying to analyze was linked to the anomalies that we were finding with the geochemistry. So for example, for the porphyry deposits, this was analyzed with the copper. And we see that several anomalies are correlated to the areas where we have high favorability for the porphyry deposits. This was the same case for epithermal deposits, the same results. So in this area, we see that the highest favorability coincides with the locations from mineral deposits of epithermal, and the validation was also done, but this time with lead. Furthermore, we had the orogenic deposits, the same case, good results, parameters that are most important. As you see, in this case, there's way more parameters. And then the mineral predictive maps with the corresponding validation with, in this case, arsenic. And finally, the intrusion-related deposits with the appropriate validation. Finally, assuming or identifying that this analysis or the results from the mineral or the machine learning were validated and can be used, then we can propose certain areas for targeting for posterior analysis and exploration. And this is really nice because if you see, for example, in this last map, it is not necessary to go to all this region and spend millions of dollars, but actually concentrate only in certain particular places. So this means that mineral predictive mapping was successfully applied for a huge area, and we can concentrate in smaller pieces of land. However, we always have to go to the field to validate this. This has not been done, but is a recommended work of the project. Also, we can relate the results from our mineral predictive mapping to known mineral occurrences. And yeah, finally, we can identify where we can localize our further investigation.